perspective of the impacts of hydrology from bulkheading. So just to set the stage straight, I'm not up here to either promote or dismiss the application of bulkheads. I'm trying to relate bulkheads to the bigger hydrologic picture in these abandoned mine settings, so folks have an understanding of what they are and how they can be applied. And again, I first want to note Kirsten Brown from DRMS is a partner in this presentation. She's most familiar with some of this bulkheading activity. So, and there's a number of other folks in this room who have worked on bulkheads far longer than I have, so technical questions will be directed at you, Kirsten.
It's definitely funky. I don't know if it's my computer.
Okay. So what I want to do is start out just kind of conceptualize what are we talking about when we talk about groundwater and mining scenarios. This is just a conceptual diagram by Christoph Goss from Deer and Alt. And so you can see a typical mountain. You can think of groundwater tables as being those blue lines. And somewhere there was a pre-existing groundwater table before any mining. And then you have faulting in the area. The faults can change groundwater, upgrading and downgrading. The fault may not match because of the permeability and movement of water, variability across those faults. So if you think about a pre-mining scenario, just look at this in terms of the brown being your existing groundwater level and the yellower color being above groundwater pre-mining. And one thing to think about is in some of those areas, given the geology's been present, say, since volcanic activity, whether we're going to say, 26 to 30 million years, that been in place. And so some of the mineralization has already happened and leaching's already occurred in metals and above that. So next, if we go into mining, we've talked a lot about it. Folks here are pretty familiar with the structure, but just imagine we start to enter, we know where these faults are. These are where the veins are. We start to go in vertically. In general, these levels are about 100 feet apart. As you go down deeper into the mine, you're going to at some point encounter water. And so that's going to start to become a player in the development of these mines. And I just like to throw in pictures here and there. So in terms of the faults that we're talking about, Brian brought this up last night. He was talking about the hanging wall and the footwall. So I just thought this was a cool picture to throw in there. This is Jeff Graves from the RMS. This is driving down on the cart in the Commodore Tunnel following the Amethyst Fault. Just to give you an idea that these faults aren't necessarily vertical structures. They often have a slope to them. So, next. So as mining continues, as I said, you're going to encounter that groundwater table. And so as you go deeper into the mine, into the subsurface, you're going to encounter groundwater. And so what happened is at some point in time, it was decided that it would be a good idea to start putting in these drainage/haulage tunnels. It was also mentioned earlier today that it's a lot easier to haul ore out when you're using gravity going downhill than uphill. So a lot of places, and I'll show some examples of where these tunnels have been put in to haul ore out, but they also provide an easy access to remove water. And again, as you continue to do that, that's going to set that groundwater table. This is a vertical view of the Creed mine complex. And jump a couple of lines there. So all I wanted to show is that this is for example, this is the Nelson Tunnel, which is another MPL site in Creed. And the Nelson Tunnel is at the bottom level of the majority of the workings. All the white you're seeing in there, that's material that's been removed from the mountainside. So kind of give you a spatial complex of how that drainage and haulage tunnel connects to different mine workings owned by different companies over time. Okay. And so other examples of where these tunnels are, if you go over to Rico, here's another great example. This is the Nelson Tunnel, which exits near the Dolores River. And just to show you the scale, the mine workings, the Argentine mine workings, are about 2 miles away from where this emergence of the tunnel is. So this tunnel, I think it's 9,800 feet between the Crosscut and the St. Louis Tunnel, where it's a long distance. So these weren't trivial tunnels, I guess to say that they go a long distance. So what happens, at the end of mining, at least in these areas, not to say mining's over, but these areas often, mines are abandoned, so the low drainage tunnel, they didn't really do anything, right? I mean, that's just, they kind of walked away and left the tunnels there, so the tunnel's still there, gravity's still working, so you're going to continue to drain. You're going to get your acid mine drainage, your metal precipitants, And the thing to remember is that over time, the structural integrity of these tunnels is going to degrade, right? Nothing lasts forever. Everything's in flux. And so often, if we think about our mine portals here, a lot of them have collapsed. We don't have that many that are perfectly intact. And so you can have collapses at the portal and collapses inside the tunnels, which then create blockages and can back up the water. And just to throw in there, I won't go into acid mine drainage, but we're going to revisit AMD. It's a water and oxygen scenario. So next slide. You can click a couple here. Material. So what is the problem? You know, this is pretty well known in this audience. Draining mines produce bad water. Just as an example, the Nelson Portal and Creed, 350 gallons a minute is not a ton of water, but all of a sudden you do the load calculations, it's 400 pounds of zinc a day to Willow Creek, and so big impairments of surface waters resulting from the release of this groundwater. Next. Here's just some pictures. I was able to help DRMS with some draining mine inventories last summer, and this is just to give you an idea of the range of conditions of the mine portals in our area. Some have been rehabbed, the bottom and the middle. The cleanest looking one is the colder, and that has been rehabbed, but there's other ones that, you know, the Porcupine, for example, in the top left, you know, completely collapsed, and so it gives you an idea of how water can be backed up in these openings. And all the way on the right is Brooklyn. Okay. So in a post-mining scenario, what you can think about is, remember, think about the bottom level. The lowest level where the mines exited is where the water was traditionally draining. And so if that is, say, a few thousand, maybe you've opened up a few thousand feet of the mountain vertically from where the historic mining water table was. You've created a lot more area where you're going to have percolating water, and you're also going to have oxygen in that environment through the mine workings, etc. And so in that area, that's potential for rocks being mineralized and metals being oxidized because of that combination of the water and the oxygen in there. And so next slide. The idea here, so to kind of get towards where we're going with bulkheads, is we talked about a plugs tunnel scenario. The idea is that you put a plug in and back up the water from that lowest tunnel, and you're going to remount that water table behind it. Can you reach the original level? Not sure. Do we know exactly what pre-existing groundwater tables are? Not exactly. But the goal is, in some cases, is to raise that water table. By doing that, you've gone from an oxidized environment to an anoxic environment. You're taking out some of the oxygen. You can help slow that production of acid mine drainage is one scenario with this plugin. So, next. So what is a bulkhead? Peter showed an example of a bulkhead. I just want to go in a little bit more so people are familiar with what it is. So a bulkhead is basically an engineered concrete wall. It can be 10 to 20 feet long, and is placed inside a mine opening to retain the water. And so what are the purposes? Well, one purpose, as we talked about, is potentially controlling reducing acid mine drainage at that location. The other thing is that it can also be used to store and control water for treatment. So example, over in Summitville, the Chandler and Reynolds have bulkheads in them that help to control, and then you can release water from them in a controlled environment at a controlled rate. The other purpose of a bulkhead, important as I showed you with those collapsed tunnels and portals, is that putting in bulkheads can help prevent blowouts. And so the ability to kind of prevent that unanticipated blowout from, say, a collapsed water is another idea, another aspect of using bulkheads. Okay. I won't go into detail because I'm not an engineer, but this is just a concrete plug, and what you can see is basically you have plywood framing to hold this. You fill with concrete, but you also want to put a pipe in there that can be used with a valve on one end that can be used to release that water, control and measure the pressure of the water behind the bulkhead. And from what I've been told is that the surface roughness of these mine tunnels create enough friction that with a plug of that magnitude, it can hold back a substantial amount of pressure. And that's all obviously engineered with this specific design. So why are we talking about this? Well, one thing that's really important for today is that in the Animas watershed in Silverton side, We already have 12 bulkheads in the Sunnyside mine workings area. Those are some of the names, the American Tunnel, etc. There's a number of other mines, the Mogul, the Red and Bonita, the Kohler, which was talked about this morning, Ransom, Sunbank. So there are existing bulkheads in there. One of the things to note is the Red and Bonita is one of the most recently constructed. It's currently constructed, but the valve is open. So the bulkhead's there, but the water's still coming out of the tunnel. And that will be a decision process to close it. And the Kohler, I think, was covered pretty well this morning by Peter. So just a quick map. This is over in Silverton. So the black squares are where bulkheads have been installed previously within the Sunnyside mine workings area. This is that American tunnel, so that long drainage tunnel which comes out in Gladstone. Moving back. So in this case, in the American tunnel, there's actually 3 bulkheads at different points along it. So not only is there a bulkhead near the portal, there's other ones along the way that are sectioning off and helping to reduce that flow. Just a couple pictures. Here's a picture of the American Tunnel Bulkhead 2 in the middle. Next, Kohler Tunnel Bulkhead. So Peter showed this morning. Just want to show you, here's your valve. And I believe that they're maybe going in and doing some upgrade or repair work on that this summer. One of the questions earlier today was how long do these last? What kind of maintenance do you have to do? And that's something that's still in progress. In every different setting, it's going to be a different scenario. But yeah, nothing lasts forever. So the thing to remember is bulkhead's not perfect. It's not going to block all the water. In the ideal situation, groundwater may be returned to the pre-mining levels. And it may exit in the natural pathways, right? So all water that came into the mountain came out in 1860 before anybody put a hole in the mountain. So understanding where those pathways are, what they were historically, is one of the challenges we're working on understanding as a holistic conceptual model of the groundwater. And if it exits through natural pathways, there's different processes with less oxygenated environments and other things, changes in the flow paths of the groundwater, so mixing of different groundwater sources may reduce the metals load in a particular discharge point that was coming out of a mine portal and then comes out naturally in seeps and springs. And I can go into that later, but residence time reductions, dilutions from different flow paths are some of the things I've been thinking about in terms of how the water would actually be better than if it just came out of the mine. Next. You click through these. So causes of leaks. If the so every scenario is different. Each bulkhead needs to be really thought through where it's placed. If you conduct it in drift workings, you're going to have a hard time sealing because there's a lot of openings and voids around it. Bad ground, you don't want to put a bulkhead in where there's a whole bunch of known fractures around that part of the tunnel, right? You're trying to look for places that are the most sturdy or consistent solid bedrock that you can find. Another one is overburden thickness. So how far into the portal do you need to go so that the pressures created by that bulkhead are also protected by your overburden. And the other thing is poor construction or grouting. So bulkheads can leak, and Peter did cover this morning that you can go back in and grout around the bulkheads to improve the effectiveness. It's not necessarily just a one-step process. And then this is a big one, unknown mining or natural structural connections to other workings. So if you plug one portal, is it going to come out somewhere else? So that's where you need to have a full conceptual understanding of not only the groundwater scenario, but the extent of the mine workings and how they're overlain with fractures and faulting in the natural flow paths. Because water movement in these mountains is through secondary porosity. It's through fractures, and it's, of course, through mine tunnels. And so you need to understand that network the best you can before you make a placement of a bulkhead. Next. Just a quick picture. So Red and Bonita, for example, choosing the location of how far in you want to put it, is relative to that overburden is what I meant by how far to create structural soundness on that. So, as I said, they can leak, and the impounded waters can maybe go back to the natural fractures and pathways, as I said, through the bedrock, that secondary porosity there. They could leak around the bulkhead and back in the tunnel, or they can preferentially flow through another pathway that concentrates the flow and doesn't really help your scenario. So every location is important, and what I want to show next is just the way to deal with leaking. So they can the pathways around these faults can be stopped with grouting. And so if grouting is not possible, in other scenarios you maybe can't bring the water level up as high. So if you have a valve on your bulkhead, you can also regulate groundwater levels behind the bulkhead in terms of where, preventing it from coming out undesirable places. So just a quick idea. So what are you talking about for grouting? This is just elaborate on Peter's talk this morning. Basically, you can think of drilling rings of grout holes around your opening and then plugging them with the grouting material to kind of shut off, those inadvertent pathways or fractures that can go around the immediate area. And then this is just the same idea. If you already have a known, say, water-bearing geologic structure, then you can also do some grouting that's targeting that to try to block that pathway. I won't go into too much detail, but we know, and this is monitored, that there is some leakage around these tunnels. Next. So this is kind of to wrap it up and bring it back to what we're doing now. Site characterization is critical to the success of bulkheading or flow control structures. And here's a pitch for some of the things we're working on now. We need to drill holes. We need to know what the water pressure is in the mountain behind the bulkhead to get a good idea of groundwater levels. Not an easy task. We ought to know things like we've installing weather stations. We understand water balance. When does water come in and out of the system? We also need to be able to monitor temporally the changes in water out of these mine tunnels. Is it consistent temporally through time? Sometimes that involves skiing up there in the winter and digging through 5 meters of snow to find the portal so you can take a measurement to make sure that the flow in the Red and Bonita in February is actually what you measured in October. So moving towards real-time continuous flow measurements at different known areas will also help us to understand how is groundwater fluctuating, say, in one mine to another. Also, just to highlight in here, your challenges in the winter. You get that snow aspect. And then this, I won't go into detail, there's also a lot of work in taking all this information and modeling groundwater three-dimensionally to understand it from this information. Okay, last few slides. Identifying blockages, as I said, in these poolings, that's the dirty work that the RMS gets to do. So knowing where these blockages occur is important before you go into a mine next. Monitoring, again, temporal variability. This is inside the Nelson in Creed. And you can see surging. You can do things like tracer injections, so actually determining if, say, water backed up in one mine tunnel ends up coming out another one. So that's applied tracers. And that's Alan Sorensen from DRMS. Groundwater, another thing that we're currently doing is in the area or vicinity of known mine tunnels that are leaking or potential areas for source controls, we need to monitor all the seeps and springs and the naturally occurring groundwater expressions in the area to see, A, what are their conditions, and to monitor them if we do these controls, will they change. This is just an idea of the Bonita Peak District. This is the Gold King Mine, Red and Bonita American Tunnel. Last fall, in a 3-week period, we sampled over 100 springs within the Bonita Peak complex to understand where else groundwater is coming out besides these red dots, which are the known draining lines. So summary, you can just put them all up. So again, you need to have access to the underground workings. You want to locate these at the lowest levels. You need to know the specific geology and radial spatial extent of your understanding for water flow, connections to other mines, and adequate overburden. There's some of the things to consider. So I think that's it, and hopefully you're at 15 minutes. Thanks.